In these slides, we will explain how we apply the principles of single path analysis to analyze multiple pathways using an adversary sequence diagram. In the depot methodology, the adversary sequence diagram is used to analyze the design of the physical protection system. An adversary sequence diagram is a graphical model used to evaluate a physical protection system. It represents every potential pathway that an adversary could take from off-site to a target, as well as every detection and delay element along each potential pathway. It is a useful tool because it allows every pathway to be compared, which assists the analyst in finding the most vulnerable path to the target. To introduce the adversary sequence diagram, we will use the simple facility characterization model, which divides the facility into 6 separate physical areas from off-site to the target area. The first step in creating an adversary sequence diagram is to list each physical area of the facility starting with off-site and ending with the target. The physical areas from the previous slide are displayed in the figure shown here. The next step is to add the protection layers between each physical area on the diagram. Each protection layer includes one or more pathway elements, detection and delay. To travel from one area to the next, the adversary must pass through one of these elements. Listed on this slide are the standard pathway element abbreviations that are used in an adversary sequence diagram. Now we will go through the process of creating an adversary sequence diagram for the example facility shown here. Each physical area is defined and pathway elements between each are indicated on the figure. For example, at this facility there is a fence, a personnel portal, and a vehicle portal separating off-site from the protected area. For this facility, the entire fence surrounding the facility is represented by one pathway element. This can only be done if the fence has the same detection and delay characteristics for the entire perimeter of the facility. If one side of the facility had a different combination of detectors or different type of fencing, both fences would need to be represented individually on the adversary sequence diagram. This would be done by adding a second pathway element between off-site and the protected area as shown. For the purpose of our adversary sequence diagram, we will assume the fence is the same around the entire facility perimeter, and therefore will only use a single fence on the boundary of our facility moving forward. To create the adversary sequence diagram, the first step is to take the 4 physical areas and the target and put them into a diagram like the one shown here. The next step is to add protection elements to the diagram. Starting from off-site, we have identified 3 protection elements: a fence, a personnel portal, and a vehicle portal. We then add these elements to the adversary sequence diagram with places to add their detection and delay characteristics. Doing this for each layer yields the adversary sequence diagram shown here. This one adversary sequence diagram represents 18 different pathways through the facility. The last step is to complete the adversary sequence diagram by adding the detection and delay characteristics of each pathway element. Keep in mind that these values depend on the equipment, skills, and tactics that the adversary uses. However, for the adversary actions that give us these detection and delay values, we can use this diagram to determine the most vulnerable path through the facility. The first path we want to find is the path of minimum detection. To do this, we look at each layer of pathway elements and choose the element with the least detection probability on that layer. So for the first layer, this would be the fence with a detection probability of 0.5. The next layer would be the 0.25 detection probability of the wall, followed by the 0.2 detection probability of the next wall. For the last layer, the target is stored in a floor vault that the adversary has no choice but to go through to get to the target. The path of minimum detection yields the best case probability of interruption for the system. So if this value is too low, we already know detection upgrades are needed. Using the same technique, we can find the path of minimum delay. For this path, the adversary still chooses to cross the fence, but then the fastest pathway is to breach both doors. He still must penetrate the vault. If the total delay on the minimum delay path is less than the response force time, we know improvements are needed with delay barriers or the response force time. The next step is to find the path where the adversary minimizes detection up to the critical detection point and then minimizes delay afterwards. On this slide, you'll see that we include the time that it takes for the adversary to cross the physical areas, such as run from the fence to the door. Typically, these elements are given a detection probability of 0.02 if there is a chance guards on patrol may see the adversary. You can see this pathway is different from either the minimum detection or delay paths, and this pathway will typically represent the worst probability of interruption path. We start by taking the minimum delay times at the target and work backwards to sum the times left after detection until it is greater than or equal to the response force time to find the critical detection point, which in this example is after the wall in the protected area. We then find the minimum detection path before the critical detection point. We then use the minimum probability of detection on each preceding layer to find the non-detection probabilities on each preceding layer and use this to calculate the probability of interruption. In these slides, we have introduced the adversary sequence diagram, which is used to compare multiple pathways simultaneously to determine the pathway with the worst probability of interruption. For each pathway, the corresponding probability of neutralization must be included in order to find the system effectiveness value for that pathway. It is important to keep in mind that the worst path is not always the path with the lowest probability of interruption, but the worst system effectiveness value, meaning the worst combination of interruption and neutralization probabilities.